Hello, class. We are covering the last section for the semester, 12.5, mathematical induction. Um, so you have a test coming up, and then after your test, you have your final exam. Okay, so 12.5 mathematical induction deals with, it's a type of proof. It's usually the first sort of formal proof that students learn how to do outside of the proofs that you did in geometry. Okay, so 12.5, mathematical induction. And we use this type of proof for like sequences, series, that kind of thing. So what I'm going to be doing here is, so I'll start off with just some vocabulary here and the basic process. And then what I'm going to do here in this video is I'll do four proofs so that you can kind of see just how the process works. Okay, so first of all, what is a proof? Okay, so it is a clear argument that demonstrates the truth of a statement beyond doubt. Okay, so what is mathematical induction? Okay, so this is a special kind of proof that demonstrates the truth of infinitely many statements by the following principle. Okay, so it's a special kind of proof that demonstrates the truth of infinitely many statements by the following principle. So it's kind of hard to imagine trying to prove one statement, let alone infinitely many statements all at once. So if you think about a sequence, and you think about, oh, well, the sum of the first two the sum of the first two terms equals this. Oh, the sum of the first three terms equals this, and the sum of the first four terms equals this. And then you start to notice a pattern. So you generalize what the sum of n terms is. So what you're basically doing is you're proving it true for infinitely many statements. You're proving that the sum is true for the first term, the second term, or the first two terms, and then the first three terms, the first four terms, first five terms, and you can go on forever and ever and ever, right? And so instead of trying to do it all by hand and showing each one is true, which is pretty much impossible because it's infinitely many terms, we use mathematical induction to prove that the sum or the formula to find the sum works for all terms, okay, or any amount of terms. Okay, so let's take a look here. For each natural number n, let P of n be a statement. And it's a statement that's depending on n. And suppose the following two conditions are satisfied. So number one, P of 1 is true. So whatever the statement is, it's true for P of 1. Okay, and suppose it is true. Okay, and then suppose that for every natural number k, if P of k is true, then P of k plus 1 is true. Okay, so if these two conditions are satisfied, then P of n is true for all natural numbers n. Okay, so that's how we prove that it's true for all numbers n. Okay, so so what happens is here we're going to go ahead and show that it's true for P of 1, and then we're going to go ahead and assume that it's true for k. Okay, P of k, and then we're going to show we're going to try to demonstrate that it's also true for P of k plus 1. If we can get this part, then we have this full sentence here. Okay, so we have this this one satisfied. Okay, so we end up assuming P of k, and then we show that P of k plus 1 is true. Okay, and that will satisfy this second condition here. So we first show that's true. We assume that it's true for k, and then we try to show that it's true for P of k plus 1. And then if we can do these things, these three things, then we have proven that it's true for all numbers n. Okay, so that's what we're going to be doing. Okay, so let's write that down. Applying the principle. Okay, so step one, we're going to prove that it's true, or show true for P of 1. Okay, and for step 2, we're going to assume true for P of k. And what we have to do is show true for P of k plus 1. Okay, so these are the three things that we do for mathematical induction. If we can show these three things, then we have used this principle here. And it says here, if these two conditions are satisfied, then it's true for all numbers n, all natural numbers n. Okay, so these are the three things we need to do. Okay, so let's go ahead and start with this first example. Okay, prove that for all natural numbers n, 1 plus 3 plus 5 plus 7 plus n terms, whatever n is, equals n squared. Okay, so over here, so we have the sequence of numbers 1, 3, 5, 7, 9, 11, 13. So the odd numbers here. Okay, so we have these odd numbers here, and we're saying that whenever you add the first n terms of that sequence, it's going to equal to n squared. So if you add the first term, well, that's just 1. That equals 1 squared. If you add the first 2, you should get 2 squared. 1 plus 3 is 4. If you add the first 3, you should get 9. If you add the first 4, you should get 16. If you add the first 5, you should get 25. If you add the first 6, you should get 36. Okay? And we can kind of see that it's true for these first 4. Okay, so we're trying to, but what we need to do is prove that it's true for all numbers. Okay? And we use math induction here. Okay, so proof by induction. Okay, so whenever you do these proofs by induction, so you always start with your statement. So let P of n equal to, and it's basically this right here. Okay, 1 plus 3 plus 5 plus 7 plus 2n minus 1 equals n squared. Okay, so we start off with our statement. And now we're going to go ahead and show that it's true for P1. Okay, so P1, that's just the first term, which is 1. Okay, and that's clearly equal to n squared. Okay, so here this works. Okay, so we showed that it's true for the first term. The first term is equal to n squared. Okay, so now we're going to fulfill that second condition. So we assume true for P of k. And what we need to do is prove that it's true for P of k plus 1. Okay, so if we assume that it's true for P of k, then when we write it out, P of k, then we get 1 plus 3 plus 5 plus 7 plus, in this case, n is equal to k. So we get 2k minus 1. And so that should be equal to k squared. Okay. So we assume that it's true for P of k. So if it's true for P of k, then we have this statement. And this statement is going to play an important role. Okay. The P of k statement, which appears in all of these proofs, this P of k statement plays a role in this third part where you have to show true for P of k plus 1. Okay. So I like to show what we're trying to prove here. So we're going to try to show that it's true for P of k plus 1. So what we're really trying to do is so here, i.e. that is P of k plus 1. So now n is k plus 1. So if I write this sum out, right, then here I'm going to get k plus 1 right inside here. And it should be equal to k plus 1 squared. Okay, so that's what I'm trying to show. I'm trying to show that this sum over here is equal to k plus 1 squared. Okay, so here's the work. P of k plus 1 is going to equal to 1 plus 3 plus 5 plus 7. Remember, k plus 1 is just 1 past k, right? So what I'm going to do here is I'm going to write the kth term. Oops, not, sorry, 2k minus 1. Okay, 2k minus 1. Okay, that's the kth term, the term that comes before k plus 1. Okay, and now I'm going to write the k plus 1 term. Okay, and what I'm going to do is I am trying to show, so you can't write this part down here because you're trying to show that this equals that. We don't know it yet, okay, but we need to show it, so we can't bring this down here, okay? So I need to work with just this written out sum, okay? So I've written it out where I include the kth term, right? And this is where this statement comes in handy, okay? We already know that 1 all the way up to the kth term equals k squared. So over here, I'm going to replace 1 all the way up to the kth term with k squared, okay? So we know this part is k squared. And then I'm just going to bring this down, okay? Okay. And what I do here now is I start working this out, and I try to work it out and see if I get that. Okay, so now I'm going to go ahead and distribute this. Okay, I'm going to combine the 2 and the minus 1. And now I'm going to factor this. And what do you know? I got this sum to look just like this. Okay, so the proof of this last part showed that it's true for P of k plus 1. The proof is here in the work. Okay, you write out that sum. Okay, and you can replace the first k terms with whatever you stated here. Okay, and then you just kind of work this out, factor, split up the terms until it looks like that, and it does. So we showed that it's true for k plus 1, and therefore we satisfy the 2 conditions. We showed that it's true for p of 1. We have that second condition here that says if it's true for this, then this is true, and therefore it's true for all n numbers. Okay, so when you're done with a proof, you can use this little black box. Okay, that's our math symbol for the end of the proof. Another one is QED. Okay, so let's go ahead and take a look at another one. Prove that for every natural number n, one plus 2 plus 3 plus 4 plus n equals to this formula. Okay, so whether you take the first term, or if you take the first 2 terms, if you take the first 3 terms, or if I take the first 100 terms, if I want to know what the sum of the first 100 terms are, I can just use this formula, plug in 100 for n. Okay, so we're going to go ahead and prove that it's true, that this is true. Okay, so proof by induction. Okay, so we start off with our Pn statement. So let P of n be 1 plus 2 plus 3 plus 4 plus n equals n plus 1 over 2. Okay. So now we're going to show that it's true for P of 1. Show true for P of 1. Okay. So P of 1 is 1 plus nothing because it's only the first term. So P of 1 equals 1. And let's show that that is equal to 1 plus 1 over 2. Okay. And here we get 1 times 2 over 2. And we see that they are equal. Okay. 1 equals 1. So there, we showed that it's true for 1. All right, so let's do this part. Assume true for P of k. Then, and let's write it out for P of k. P of k is 1 plus, here, let's bring this down so we can see. Okay, 1 plus 2 plus 3 plus 4 plus, now we're replacing all the n's with k. So we're going to put k here. And we're going to put k times k plus 1 all over 2. Okay, so we're assuming that it's true for P of k. If it's true for P of k, then when I plug in k, I can plug in k here. Okay. So now what I need to do is I need to show true for P of k plus 1. Okay. That is 1 plus 2 plus 3 plus 4 plus k plus 1. Replace now all the n's with k plus 1. So I'm going to have a k plus 1 here and a k plus 1 over here, all over 2. Okay, this is what we need to show what the left-hand side looks like. So we're going to start off with the left-hand side. We're going to work that left-hand side until it looks like this. Okay. Okay. All right, so P of k plus 1 is equal to, when I write this part, so up here, I didn't include the kth term, the one just before k plus 1. But when I do my work, I will, so that I can use this statement and you can see how I'm able to. Okay. 1 plus 2 plus 3 plus 4 plus. So here, I'm going to include the kth term, which is the one before k plus 1. And here's the k plus 1 term. Okay. I can't touch this. I leave this here so I can see my work and I know I can see what I'm trying to get my work to look like. Okay. All right. Okay. So again, right here, you already know that the formula works for the first k terms. So the first k terms can be rewritten like this right here. Okay, and I'll go ahead and bring down this plus k plus 1. Okay, so now I have fractions, so I'm going to go ahead and multiply this one by 2 over 2 so that we have common denominator. Okay, so now we have common denominator, so I can multiply these out and combine them. So here I get k squared plus k, and over there I get 2k plus 2, and it's everything over 2. Well, at least we have the 2 part. Okay, so now we got to work with this top part. Okay, so I can combine the like terms, k and 2k. Gives me 3k. And I can factor that out. K and k plus 1 and 2. Okay. You probably want, if you have a k plus 1 factor, you probably want that one first because generally it's out in the front somewhere. Okay. Okay, so let's see. This is what I have, and this is what it needs to look like. Let's scroll up a little. That's what I have. Okay. I have the k plus 1 part. I have the 2. I need this factor, k plus 2, to look like this. If I simplify this one up here, removing the parentheses, I end up with k plus 2, right? Okay, so all we need to do is split this 2 up as 1 plus 1. Okay, and we're done. And here we have it. We show that this does equal to this right-hand side up here. We showed that this side, the left-hand side, does match the right-hand side, so we are done. End of proof. Okay. So hopefully you're starting to see it. Okay, so let's do a third one. Prove that for every natural number n, one plus 4 plus 7 plus 3n minus 2 equals n 3n minus 1 all over 2. Okay, so we need to prove that this is true for all natural numbers. Okay, so proof by induction. Okay, so we start with our P of n statement. One plus 4 plus 7, which is the very thing that we are trying to prove. Okay, and then we show that it's true for P of 1. Okay, so P of 1 equals 1, right? It's just the first term. And let's show that it's equal to 1 when we plug into the right-hand side. Okay, so we get 1 times 3 minus 1, and we get 2 over 2, which is 1. Okay, so it works for 1. Okay, So now we assume true for P of K. So then let's write that one out. P of K. P of K, which equals to 1. So now we're replacing all the n's with K. 1 plus 4 plus 7 plus 3K minus 2 should equal to, again, replacing all the n's with K. We get K times 3K minus 1 all over 2. Okay. So this is what we're going to be using when we try to prove that it's true for P of K plus 1. Okay, so we assume true for P of K, so now let's show that it's true for P of K plus 1. Okay, i.e. 1 plus 4 plus 7 plus, now replace all the n's with K plus 1. 3K plus 1 minus 2 equals K plus 1, 3K plus 1 minus 1 all over 2. Okay. So you can see here, instead of, this is normally where the n's are. So now I replace them with K plus 1. So I replace it with K plus 1, K plus 1, and K plus 1. Okay, so we need to show that this side matches this side. Okay, so let's see how we can do that. 1 plus 4 plus 7 plus, here I'll include the kth term, which is 3K minus 2. And now the K plus 1 term, the term that comes after K. Okay. So again, don't touch this. Leave it there. That's more like that's your goal. Okay. You're trying to manipulate this left-hand side so it looks like that. Okay. All right. So this part is the first K terms. So we can rewrite it as this right here. 3K minus 1 all over 2 plus 3K plus 1 minus 2. Okay. Let's see here. Okay, I'm going to clean this up right now. I'm going to go ahead and let's just go ahead and distribute everything, both of these. Okay, so before we get our common denominator, 3K squared minus K all over 2. And this one is going to be 3K plus 3 minus 2. Okay. And I can combine those two like terms. So I get 3K squared minus K all over 2 plus 3K plus 1. Okay, so now I can get my common denominator. Okay, so I need to multiply this side by 2 over 2. So now we have common denominators here, so we can combine these two fractions. Okay, so let's see what we get here. 3K squared minus K plus 6K plus 2 all over 2. Okay. Combine the negative K plus 6K. All right. And let's go ahead and see if we can factor that. Okay, so k times 3k plus and plus, and 2 and 1. So 2 and 1, and this will get me the 5k in the middle. Okay, so let's have a look. We have the k plus 1, we have the 2. We're going to have to fiddle around with this factor here. Let's see what it needs to look like. 3 times k plus 1 minus 1. If I distribute all of this, I get 3k. 3 minus 1 is 2. 3k plus 2. And that's what we have here. Okay, so we can just rewrite it like this. So we have the k plus 1 part, we have the 2 part, and I can rewrite that as 3 times k plus 1 minus 1. And if I do that, I will still get the 3k plus 2. 3k, 3 subtract 1 is 2. Okay, but now this one, the way it's written like this, matches this right-hand side. Okay, so we showed that it's true for k plus 1, and we satisfied both conditions. It's true for 1. It's true for that if it's true for k, then it's true for k plus 1. Okay. Therefore, it's true for all natural numbers. Okay, so let's go ahead and take a look at one more. If you already get it, you can go ahead and start on your homework. Or you could try this one. Hit the pause button and see if you are able to get the same thing. Okay, prove that for every natural number n, 1 squared plus 2 squared plus 3 squared plus n squared equals to n times n plus 1 times 2n plus 1. All over 6. Okay. All right, so let's go ahead and prove this. Proof by induction. Start with your PN statement. 1 squared, the thing you're trying to prove. 1 squared plus 2 squared plus 3 squared plus n squared equals n times n plus 1 to n plus 1 all over 6. Okay. Now assume show true for p of 1. Okay, so p of 1, the first term is 1 squared, which equals 1. Okay, and if I plug in 1 here, do I get 1? Let's see. 1 times 2 times 3 all over 6, and we can see that we do. Okay, we get 6 over 6, which is indeed 1. Okay, so we showed that it's true, or that it works for 1. Okay, all right, so now we assume true for p of k. Assume true for P of k. Then, and let's write it out, P of k, which would equal to 1 squared plus 2 squared plus 3 squared plus k squared should equal to k times k plus 1 times 2k plus 1 all over 6. Okay. And now we have to show or prove that show that it's true for k plus 1. So we're trying to show that 1 squared plus 2 squared plus 3 squared plus k plus 1 squared should equal to k plus 1, k plus 1 plus 1, 2 times k plus 1 plus 1, all over 6. Okay. A little more complex looking over here. Okay. But that's what we have to get this side to look like. Okay, so let's see what we have. All right, so here's the work. P of k plus 1 equals 1 squared plus 2 squared plus 3 squared. Here I'm going to include the kth term, k squared, and now the k plus 1 term, k plus 1 squared. Okay, and stop there. Don't touch that, don't bring that down. Now you have to work with this to get it to match with that. All right, so this here is the sum of the first k terms. And we know from the statement that's here, we know from the statement right here, that the sum of the first k terms equals this. So let's go ahead and rewrite this part like that. Okay. And then I'm going to bring this one down. Okay, so let's see. All right, so one way to do this, you could try multiplying this out and see if you can manipulate it that way. What I'm going to do, because I noticed that, oh, this has a k plus 1 and so does this. So both of these terms here, this here and this one here, both have k plus 1 in common. So I'm going to go ahead and factor out a k plus 1 because they both have k plus 1. So I'm going to go ahead and factor out a k plus 1. I might need to have brackets here to keep things organized. And so over here in the first term, I'll need a k and a 2k plus 1 over 6. And then over here, I'll need just 1 k plus 1. Okay. Okay, so that's a little better. Okay, so now I'm going to go ahead and get my common denominators so I can work with the inside of those brackets. So I'm going to multiply this by 6 over 6. Okay, so let's go ahead and multiply that all out. I'm going to leave this here, which is nice because we do, if we look back up here to see what we're trying to get, we do have a k plus 1 out there, so that's good. All right, so 2k squared plus k plus 6k plus 6 all over 6. Okay. Keep that out there. And now I have 2k squared plus 7k plus 6. Okay. And now I'm going to go ahead and factor that trinomial on the inside. All right, so 2k and a k, both of them positive. 6, a 3 and a 2. Where do I want them? 3, 4, 5, 6, 1. Okay, so we want the 3 here and the 1 here. Okay, and that will give me 7k for the middle term. Okay, so this is what I have, factored form. So now let's have a look at what we're trying to make it look like. I have a k plus 3. Let's take a look. Do we have a k plus 3? Oops. That was a 3 times 2. What am I looking at? Okay, so we're trying to make 6, 3 and 2, or 6 and 1. 6 and 1 doesn't work. 3 and 2. 2 here, 3 here. That gives me 4 plus 3. That's 7. Okay, that works. Okay, so let's take a look. Okay, so this factors out to k plus 2, 2k plus 3. And let's take a look up here. Okay, so we have a k plus 1 plus 1. That's our k plus 2 part, right? So I can definitely rewrite that. Okay, so let's do that now. So k plus 1 plus 1. Okay. And we do have the 6 part as well. All right. And let's take a look at this one. 2k plus 3. And we want it to look like, so we have 2k plus 3. Oh, okay. And we want it to look like this. Does this equal 2k plus 3? 2k, 2 plus 1 is 3. 2k plus 3. So yes. So let's just go ahead and rewrite it like that. 2 times k plus 1 plus 1. And so here, the left-hand side does match up with the right-hand side. So we are done. We have proven that it is true. Okay. All right. So that is it. And that is the final lecture for this semester in this class. All right. I hope you are able to keep up with your homework and that you have enough time to study for the tests and also study for the final exam. And I hope you enjoyed this course with me. Again, if you have any questions, email me or text me.